on to chapter 5, and we're going to start by doing some review. So I've called it 5.0 review. Some of this review is from earlier in the course, and some of this review is from previous years of mathematics. So let's start by talking about even functions. We did this at the start of the course, and what you might remember is with even functions, what needs to be true is that f of x is equal to f of negative x. And there's symmetry about the y-axis if you were to graph it. And I'll give you some examples in just a second, but let's go on to odd functions. With odd functions, what's true is that negative f of x is equal to f of negative x. And with odd functions, they have origin symmetry. So the graph looks the same when you rotate it 180 degrees. So what we're going to do is we're going to figure out for these 5 cases, 2 functions that are written and 3 that are drawn. We're going to figure out whether they're odd, even, or neither. So when it's written like this, what you want to do is you want to put negative x into the function. So it says y equals, but probably what I should have written is f of x. I mean, it's the same thing more or less, right? But since what my point here is that you need to put negative x into there, I think it might make it a little bit easier for you to understand. So let's do this. Let's figure out what's f of negative x. And if you put f of negative x, that's what that means is you got to put negative x in this x, so you have negative x cubed, and you need to put negative x into this x. Okay, if we simplify that, negative x all cubed, well, that's 3 negatives, so it's going to be negative x cubed, and then negative x is plus x. So this is what f of negative x equals. Okay, so what we want to do is we want to compare our answer right here. We want to compare that with this answer. Are they exactly the same? No, they're not. Is this highlighted one down here, is this the negation of that one? Yeah, it is. It's absolutely equal to the negation of what we started with. So what does that mean? That means that f of negative x equals negative f of x. And that means it is an odd function. Okay, let's try the next one here. So again, I'm just going to change this to f of x, and we're going to put negative x into the function. So f of negative x equals the absolute value of negative x, just plug in negative x into that x there, minus 4 times negative x to the 6th power. So if we simplify that, absolute value of negative x is just x, or you could still write it as absolute value of x, that's fine, minus 4 negative x to the 6, well that's 6 negatives, so it's going to be positive, and then just x to the 6. So what do you notice if you compare this with this? They're exactly the same. In other words, f of x is just exactly the same as f of negative x, which means it is an even function. Okay, let's move on to the graphs here. So in this one, the first one here, we definitely have some symmetry. We have some symmetry over the y-axis, right? If there was a mirror right here on the y-axis, then the right-hand side would fall exactly on the left-hand side. So that is, right here, symmetry about the y-axis. This is an even function. For the second one, there's symmetry again. This is origin symmetry. If you were to rotate this is hard for me to do, but if you were to stand on your head or rotate this 180 degrees, this part of the function would fall exactly on that part, and vice versa. So this is odd symmetry, or sorry, this is an odd function here because it has origin symmetry. And this one, well, if you rotated it, it wouldn't look the same, and if you reflected it over the y-axis, it wouldn't look the same. It's not even nor odd. It is neither. And this is what you need to know about odd and even functions. Okay, intercepts. Definitely done a little bit of this year, and a lot in previous years. Intercepts are, of course, where a graph crosses the x or y. That should not say intercept there, so let's change that. That's a mistake. This should say where a graph crosses the x or y axis. And what we're going to do here is we're going to find the intercepts of the following curves. So let's start by getting the y-intercept. So what's true for every y-intercept? Every value that's a y-intercept has an x value of 0. So what you need to do is you need to plug 0 into the x's. So if we do that, we'll get y equals 0 squared minus 1 over 0. this is a problem because we're now dividing by 0. So you're not allowed to do this, which means what? That means there is no y-intercept. Okay, let's get the x-intercept. In order to get the x-intercept, what we know is true about every x-intercept is it has a y value of 0. So this time we're going to put 0 into the y. So we have 0 equals x squared minus 1 over x, and we're going to solve this. Why don't we start by multiplying both sides by x? When we multiply this side by x, they'll just cancel, so that's good. When we multiply this side by x times 0 is just 0. So now we have 0 equals x squared minus 1. Hey, it's a quadratic. How do we solve quadratics? We set it equal to 0, perfect, and then we factor. Or you could also use the square root method here and move the 1 over. You can do it that way as well, but I'll factor. So it's a difference of squares. We're going to have x plus 1 and x minus 1, which means our answers are x equals negative 1 and x equals positive 1, or you could put plus and minus 1. So these are your x-intercepts, or the way you could also write them as points if you want. You could write that one x-intercept is 1, 0, and the other x-intercept is negative 1, 0. That's fine as well. It's not necessary you do that though, as long as you know you're talking about the x-intercepts. Plus or minus 1 would also be okay. Okay, same sort of thing over here. In order to get the y-intercept, we put 0 into the x's. So you're going to have y equals 0 squared plus 0 minus 4, which means y equals 4. So there's your y-intercept. If you want to write it as a point, you would put 0 in for the x, and 4, oh sorry, I put 4, it should be negative 4 of course, sorry. So you'd have your point as 0, negative 4. Okay, and for the x-intercept, same thing, we're going to put 0 into the y. So you have 0 equals x squared plus x minus 4. It's quadratic, make it equal to 0, we did, and we're going to factor. So to factor, we're looking for two numbers that multiply to 4 and subtract to 1. Multiply to 4, subtract to 1. Wait a minute, there's no such numbers. Uh-oh, what do we do now? Well, people, what you do now is you do x equals negative b plus or minus square root b squared minus 4ac, all divided by 2a. Yes, you must use the quadratic formula. So let's do that. We have got x equals negative b, well that's negative 1, there's a 1 right there. Negative 1 plus or minus the square root of 1 squared minus 4 times a, which is also 1, times c, which is negative 4. All divided by 2 times a, which is 1 again. So simplifying that, you get negative 1 plus or minus square root. Okay, 1 squared is 1. 4 times 1 times negative 4 is negative 16. So be careful here. You have minus negative 16. All divided by 2 times 1 is 2, which means x equals negative 1 plus or minus the square root of 1 take away negative 16 is 17 all over 2. These are your x-intercepts. There's two of them, right? If you want to write them as points, one would be negative 1 plus root 17 all divided by 2, comma, 0. And the other one would be negative 1 minus root 17 divided by 2, comma, 0. There are your 2 points. Okay, next we're going to divide polynomials. So we have a cubic here, and we're dividing it by a quadratic. The only way you're going to be able to divide these is by using long division, I'm afraid. If you're dividing something like this, where it's of the form x plus a or x minus a, then you can use synthetic division, which we'll get to in a second. But for here, you have to use long division. So how do we do that? Well, first of all, just like in your elementary days, you're going to put this out front, this inside, right? So this is going to go out front, but be careful. You're going to write x squared plus 0x, right? There's no x's there, no term, an x term, but you need to include it, 0 of them, plus 3. And similarly here, you have an x cubed, you have minus 5x squared. There's no x's here too, there's no x term. So you need to put plus 0x minus 15. Just make it a lot easier when you're actually doing the question if you have it in descending order with all the different terms. All right, let's start. You just look at the first term here and you ask yourself, what do we have to multiply x squared by to get x cubed? You need to multiply by x. So right over the x here, I'm going to write x, and I multiply. X times x squared is x cubed. X times 0x, and that's weird, but that's like 0 times 1, which is 0, and then x times x, which is x squared. So you get 0x squared. X times 3 is 3x. And then what do we do now? We subtract, and we subtract the whole thing. So be careful. You have x cubed minus x cubed, which is nothing. You have negative 5x squared, take away 0x squared. Well, that's still negative 5x squared. And you have 0x, take away 3x, which is negative 3x. What do you do next? You drag down the negative 15, and we do this whole process over again. You ask yourself, what do I need to multiply x squared by to get negative 5x squared? I need to multiply by negative 5. So I'm going to multiply everything by negative 5. Negative 5 times x squared, negative 5x squared. Negative 5 times 0x is negative 0x. Negative 5 times positive 3 is negative 15. And what do? Subtract. Negative 5x squared, take away negative 5x squared, 0. Negative 3x, take away 0 is still negative 3x. Negative 15, take away negative 15 is 0 as well. So this is it. We have our answer. This part up here is called the quotient. Right? The quotient is your answer when you divide. And this part right here, what's this called? This is the remainder. That's what's left over when you do that division. Now I know that's not many people's favorite thing is doing long division. You will have to do it a little bit in this chapter, not too much, but you will need to know how to do that. What people prefer more is synthetic division. Now, if you do like long division, you can use long division again right here. But if you have it in this form, this x minus a or x plus a form, you can use synthetic division. Remember how to do it? I always say that you draw like a flagpole sitting on the ground. And what you write across here are your coefficients here. So you have the coefficient of 2, you have a coefficient of negative 1, you have a coefficient of 3, and again you have to do them all. You have an x cubed, an x squared, an x to the first. Where's my constant? I got to put a 0 here to represent the constant. That's kind of missing there. What number goes in this on the flag here? The number goes in is, if this is x minus 4, like that's your factor, you put what the root would be, which is 4. If this was x plus 4, you'd put negative 4 here. Now, how does this work, this synthetic division? You drag down the first number, so I write it here, and I multiply. 4 times 2 is 8. Then I add, and it's kind of weird that you're adding instead of subtracting this time, but I add, which gives me 7, and I multiply, which is 28. And I add, which is 31, and I multiply, which is 124. My goodness. And I add, and I get 124. Okay, I got 4 numbers. What does this mean here? Well, the first number will always be your remainder. Next one will be your constant, or your x to the 0 power. Then comes your x to the first power, and your x squared. So if we're going to write the answer, we would have 2x squared plus 7x plus 31, and then you have a remainder. I'm just going to write it like this, with a remainder of 124. That's a 4. And now a few things that we did earlier in the course. We actually started chapter 5. I don't know if you remember, we did 5.1 and 5.2 when we were working on chapter 1. So we're going to go back and review a few things here that people sometimes have difficulty with. Vertical asymptotes. You can find them by determining values that make the denominator equal 0. And horizontal asymptotes, you're going to find by computing the limit at infinity. So I think we're going to have to give some examples here to really solidify this. We're going to find the asymptotes of this function, y equals 2x divided by x squared minus 4x minus 12. So let's start by finding the vertical asymptotes. So just as it says here, what you're going to do is you're going to see what makes the denominator, x squared minus 4x minus 12, what makes that equal 0? Okay, it's quadratic, set equals 0, and factor. And we can do that. Two numbers that multiply to 12 and subtract to 4 are 6 and 2, so we have x minus 6, x plus 2, which means x equals 6 and x equals negative 2 are our two vertical asymptotes. Those are the equations of the two vertical asymptotes. Now, something else that we wanted to do, or that we did before, is we want to know what the tendency is of the graph near those asymptotes as they approach the asymptotes from the left and as they approach them from the right. So I'll show you what I mean here. If this is our graph, so here's our coordinate plane, and then if I go out to 1, 2, 3, 4, 5, 6, and -1, -2, I know that I have asymptotes here. Vertical asymptotes, that is. So there's one there, and there's one there. And what I want to know is, what does the graph do as it approaches this asymptote from the left? Does it go up towards infinity or down towards negative infinity? Same from the right here. Does it go up towards infinity or down towards negative infinity? Same to the left here, infinity and negative infinity, and same from the right there. So there's actually 4 places we have to look. It's a bit of a drag, I'm not going to lie to you. So again, let's call this f of x just to make this a little bit faster. This is f of x. So what I'm interested then is I'm interested in the limit, remember this? The limit of f of x as x approaches, let's start with this one here, where it's 6 here, as x approaches 6 from the left-hand side. And in fact, it's going to be easier if we also rewrite this just in factored form. So you see how we got the factored form x minus 6, x plus 2? This is what we're going to look at now. We're going to ask ourselves with our fuzzy math, what happens when we put a number just a little bit less than 6, like 5.99999? What happens when we put that into this highlighted bit here? Okay, let's do it. If we put something a little bit less than 6 into the numerator, well, basically you can just put 6. It's so close, you could just put 6 in there. 2 times 6 is 12. Okay, I'm just going to put positive. It's a positive number. 12 is a positive number. Now, if I put a number just a tiny bit smaller than 6, 5.9999, what happens when I subtract 6? You're going to get a number that's just it's a tiny number, but it's going to be negative. So what we end up with in the first bracket is a small negative. And then in the second bracket, we have 6 plus 2, which is 8, which is another positive. Okay, let's simplify this. We've got a positive on top, and then we've got a small negative, like really small negative, times a positive. So you're going to end up with a very small negative times positive is negative. And then, if you divide a positive number by a really small number, what happens? You get a giant number. And since it's positive divided by negative, it's going to be a giant negative number. In other words, it's going to tend towards negative infinity. So I know with this graph that on the left-hand side of 6, it's going to tend down to negative infinity like that. Okay, let's do this 3 more times. Let's do the limit of f of x as x approaches 6 from the right. Well, on the top, we can put 6 in there. 2 times 6 is 12, which is positive. On the bottom, 6, a little bit bigger than 6, 6.0001. If you take away 6, you get a very small positive number. And then you're going to multiply that by 6 plus 2, which is 8, which is also positive. So everything's positive here. You have a positive divided by small, really small number times another number gives you a very small number. And it's going to be a small positive since they're both positive. A number divided by a very small number gives you infinity again, but this time it's going to be positive infinity because, positive infinity because positive divided by positive is positive. So I know on the right hand side it's going to look something like this, going up towards infinity. Okay, 2 more times. This time we're going to look on the left and right hand side of -2. So the limit of f of x as x approaches -2 from the left. Okay, so if I put -2 in here, 2 times -2 is -4, I get a negative. I don't know why I didn't put equals there. So I get a negative divided by, I can plug -2 in here as well. -2 take away 6 is -8, so I get another negative. And I'm going to multiply that by a number just a little bit smaller than -2. That's -2.0001 or something. If I add 2, do I get back to 0? Not quite. So I'm stuck with a very small negative. And then if I multiply the bottom, I'll still have this negative on the top. A small negative times a negative gives me a very small positive. And finally, when I divide this, a number divided by an extremely small number tends towards infinity, and negative divided by positive is negative. So I get negative infinity here. So as the graph approaches this vertical asymptote from the left-hand side, it's going to approach negative infinity. It's going to go down like this. And you can probably guess for the last one, but let's just finish it off. The limit of f of x as x approaches negative 2 from the right equals, so obviously the top, if I put negative 2 in here, 2 times negative 2 is negative 4, it's negative. If I put negative 2 in here, I get negative 8, which is another negative. So just like we have here, I'm going to have a negative and a negative. I'm going to multiply that by, okay, a number a tiny bit bigger than negative 2. That'd be like negative 1.999999, and I add 2. Well, that's going to go just a tiny bit above 0. So it's going to be a very small positive number. Small positive equals negative on top. Negative times positive is negative, and since we're multiplying by a very, very small number, it's still going to be small. So you get a small negative. Divide a number by an extremely small number, and it gets really, really big, like all the way up to infinity. And negative divided by negative is positive. So on this side, as you would expect, it's going to go up towards positive infinity. All that, and all we've done so far, is the vertical asymptotes. Now we need to do the horizontal asymptotes. Okay, and what it says here is you're going to find by computing the limit at infinity. So in other words, what we need to figure out here is what's the limit of the function as x approaches infinity, and also negative infinity, so plus and minus infinity. We got to figure out what those equal. So there's two ways to do that. The very quick way you can do that, remember, is you could look at the degree of the numerator and denominator, and since the degree of the denominator is bigger than the degree of the numerator, then we know that the horizontal asymptote will be at y equals 0. That'll always be the case if the denominator has a bigger degree. But if you forget that, the other way you can do it is you divide each one of these terms by the biggest degree. So the biggest degree is x squared. So I would go 2x divided by x squared over x squared divided by x squared minus 4x over x squared minus 12 over x squared, which means we'd have the limit of f of x as x approaches plus and minus infinity. Okay, 2x divided by x squared, well, you'd still have a 2 over x here, and then x squared over x squared is 1. You'd have 4 over x here and 12 over x squared here. And then remember, we had this limit that whenever you divide a number by an enormous number like infinity or negative infinity, what does it come close to? If I divide 2 into an infinite number of parts, I mean, if infinite's too big, think if I divided 2 by 1 billion. How big is each one of the pieces when I divide it into a billion? Tiny. So tiny. In fact, this limit is going to approach 0. So what you're going to get here is 0 over 1 minus, oh, we're cutting 4 into an infinite number of parts, 0 minus, we're cutting 12. I mean, when I do infinity squared, I still have infinity, and 12 divided by infinity is 0. So what I end up with is 0 over 1, which equals 0, which is exactly what I said. Remember, I said that if the denominator has a bigger degree than the numerator, you'll always have an asymptote at y equals 0. So here's our horizontal asymptote. By the way, what if the numerator's degree was bigger than the denominator's? What if it was like 2x cubed over x squared minus 4x minus 12? Then there would be no horizontal asymptote. And one last question, what if they were exactly equal to each other? What if it was 2x squared over x squared minus 4x minus 12? Then you look at the leading coefficients in the numerator and denominator, so it'd be 2 over 1. So your asymptote would just be at 2, obviously. 2 over 1 equals 2, so your asymptote would be up here at 2. Okay, one last thing, very, very quick, don't worry. What are the intercepts here? To get the y-intercepts, you'd be putting 0 into the x's, so you'd have 2 times 0, which is 0, divided by 0 minus 6, which is negative 6, and 0 plus 2, which is 2. So you get 0 over negative 12, which is just 0. So your y-intercepts, or y-intercept, I guess, is at 0. So you have a point right here. And to get the x-intercepts, you'd be putting 0 into the f of x or 0 into the y. Then you could multiply by the whole denominator, so you'd be left with 0 equals 2x. And if you divide 0 by 2, you still have 0. So, I mean, it makes sense. Your x-intercept is also 0. But you should still do that step, by the way, just to make sure you don't have multiple x-intercepts. But in this case, you don't. So you can probably assume that the graph goes something like this down here. And this is why we're doing all this. You're going to learn to graph very, very complicated functions in this chapter. So all this stuff we've done down here, you will have to do this. Okay, that's the end of the review.
You're giving me the sweet